Hi friends, today we are going to discuss about the topic finite state automata as a part of the course Formal Language and Automata Theory. My name is Monica and this course Formal Language and Automata Theory is a very important course in every engineer's life. So without any late, let's go into the topic. Finite automata. Finite automata is the simplest machine to recognize patterns. The finite automata or finite state machine is an abstract machine that has 5 elements or tuples. It has a set of states and rules for moving from one state to another, but it depends upon the applied input symbol. Firstly, automata. Automata is again divided into finite automata, push-down automata, Turing machine. In this presentation, we are going to discuss about finite automata. So, finite automata is again divided into finite automata with output and finite automata without output. In finite automata with output, we have two types, Moore machine and Mealy machine. FA without output, we have DFA, NFA, Epsilon NFA. In this presentation, we are going to discuss about DFA, NFA and conversion of NFA to DFA. Here we go. DFA. DFA means deterministic finite automata. Deterministic refers to uniqueness of the computation. The finite automata are deterministic finite automata. If the machine reads an input string one symbol at a time, in DFA, there is only one path input from the current state to the next state. Yeah. Here is an example for DFA. So, formal definition of different automata. So, DFA. A deterministic finite automata is a collection of defined as F5 tuples and is as follows. M equals to Q, sigma, delta, Q naught and F. Q refers to finite set called states. Sigma refers to finite set called alphabets. Delta refers to Q cross sigma, that is Q. It is a transition function. Q naught refers to the initial state, F refers to the final or accept state. Graphical representation of DFA. Yeah, the state is represented by vertices. The arc labeled with an input character shows the transition. The initial state is represented with an arrow and the final state is represented by double circle. Yeah. Trap state or a dead state in DFA. What is meant by this state? Yeah, if a transition goes to a state from which it can never escape, such a state is called a trap state or a dead state. It is called dead state. Yeah. In the above example, Q2, here we can see Q2, right, is a dead state because it cannot reach the final state. Here, initial state is Q0 and Q1 is the final state. If a string to be accepted here should go to the final state, but if we give input B at Q0 state, it will directly goes to Q2. Here we can say that from Q2 it cannot reach to final state Q1. So Q2 is the dead state for this DFA. And we can observe only one output A is going to the next level and B is going to the next level. No another B and another A can be existing for Q0. This is known as DFA. And application of DFA. The different applications of deterministic finite automata are as follows. Protocol analysis, text parsing, video game character behavior, security analysis, CPU control units, natural language processing, speech recognition, etc. So guys, let us see an example for DFA and I'm going to explain DFA. So in this DFA, we are going to learn about this DFA. So DFA is deterministic finite automata. It is the simple model of computation. It has a very limited memory. So from this DFA, we are going to write Q, sigma, Q naught and F. Here, capital Q contains set of states. Here, set of states are A, B, C, D. So, these are set of states. Sigma represents set of inputs. So, sigma, we are having 0 and 1. Set of 0 and 1. Set of inputs. Then, we have delta. Delta represents the Q cross sigma implies Q, which is the transition table. We'll be discussing it in transition table. So Q naught is initial state. Here we can clearly see that A is the initial state because it is represented by arrow, and F is the final state because it is double circled, represented with double circle. D, final state is D. After seeing a DFA, we have to write Q sigma delta Q naught F. So here we have written the first step, then we go to the final step, transition table. So transition table for the given DFA can be drawn very easily, don't worry. Transition table, which is denoted by Q cross sigma implies Q for DFA. So this is the transition function of DFA. So now we are going to draw the transition table for the given DFA. First, we have to see for each state where it is going when the input is 0 or 1. For A, if 0 is the input, it is going to C, and A, if 1 is the input, it is going to B. In the same way, for every state, we are going to write the transition table. And now, we are going to draw the transition table. First, write the states Q. For Q, we are having 4 states A, B, C, D. A is the initial state because it is represented by arrow, and final state can be represented with star or circle. So final state is D. So 0 and 1 are the inputs. So now clearly observe and write the where the state goes. If 0 is input, it goes to C. If 1 is the input, A goes to B. If 0 is the input, B goes to D, which is the final state. If 1 is the input, B goes to A. If 0 is the input, C goes to A. If 1 is the input, C goes to D. If 0 is the input, D goes to B. If 1 is the input, then D goes to C. This is our transition table for the given in DFA, and we can draw it very easily. Now I hope you got a clarity how to draw transition table for the. Here comes the second example for construction of a DFA. So the question is, construct a DFA which accepts the following language. The language is L1 equals to set of all strings that starts with 0. So let us take some examples for this, like 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, and so on. So these are the some example strings for the given language. So I'm taking initial state as A. If it is input is 0, then it will reach the final state B. So if 1 is the input at A, initial state A, then it will reach C, which is the dead state. C is a dead state here because the string should not start with 1. It should start with 0. So it will reach a dead state from which it can't reach a final state. So C is here dead state. For B, input 0 1 reaches the same state B, and for C, input 0 1 reaches the same state C. So I have written in the same way how we'll write the Q sigma Q naught F. Here Q are having A B C, sigma is having 0 1, Q naught is having A, where initial state is A, and final state is B. So Q states Q are A, B, C. A is the initial state and B is the final state. 0, 1 are the inputs. So here we are going to draw the transition table. If 0 is the input for A, it will reach B. If 1 is the input for A, then it will reach C. If 0 is the input for B, it will reach the same state B. If 1 is the input, then it will reach the same state B. For C, both the input will reach the same state C, where C is the dead state here. Now we are going to test for some strings like 001 and 101. So our machine should satisfy the given condition. So here our initial state is A. So delta of A comma 0 goes to delta of B comma 0. So delta of again B comma 0 means at B it will reach B again, B comma 1. If B comma 1 means it will reach the B is the final state. So 001, this string is accepted. So machine accept this string because it started with 0. Next example is 101. At A comma 1, it reaches the C, which is a dead state. So from C, 0 comma 1 reaches the same state C, but it is not a final state. So this string is not accepted. That's it. Construct a DFA that accepts any string over AB that does not contain the string AABB in it. This is the final example for DFA. So let us try to solve this. So string does not contain AABB. We have to design a DFA that does not accept a string having AABB. So now to make this problem easier, I am going to take a simpler method. First write the inputs AB, and I am trying to design a simpler problem. Let us construct a DFA that accepts all strings over AB that contains the string AABB in it. So what he asked does not have, but I am constructing a DFA that is having AABB. So construct a DFA which contains or accepts AABB, string having AABB. So I'm constructing a DFA. Initial state I'm taking as A. So if I'm giving A, then it should move to next state B. If again I give A, then it should go to the next state B. At the state A, if I give B as an input, it should be remaining in the same state. And at B, if small b is the input, then it should go to the A. Yeah. So A, B, B is our input. So if B is the input, then it reaches the same state. So again A, B, B cycle starts. So at C, if B is the input, it goes to the next state D, and at D and at C, if A is the input, it remains in the same state. At D, if B is the input, then it will reach as the final state E. At E, AB is the input means it will be remaining in the same state, final state E. So if A is the input at D, then it will reach as the B, because at that we can start our cycle AABB again. This is our final DFA, but this is not what we want. So we want a DFA which does not accept a string having AABB, but this accepts. For that, we have to flip the states. Flipping means make the all final states into non-final states and all the non-final states into final states. So here we should make final states into non-final states and non-final states into final states. So A, B, C, D are non-final states. So I am writing A is final state in my required DFA because it is a non-final state in before DFA. So B is also a final state now. C is also a final state. D is also a final state. E is non-final state because in our DFA it is a final state. Don't do any changes in the inputs. Inputs should be the same. So don't make any changes in your inputs. And this is the final DFA what we want. So this is DFA does not accept a string containing AABB in it. So this is the required DFA and that is all about the DFA construction. I hope you all understood the DFA part. So we have already learned how to draw the transition table for a given DFA. Let us see for this given DFA how to draw the transition table. First we have to take all the states Q0, Q1, Q2. We have already identified Q0 as the initial state because it is represented by arrow and Q2 is the final state because it is represented by double circle and I have represented it as arrow and star with the final state. If 0 is the input for Q0, it goes to Q0 again. If 1 is the input for Q0, then it goes to Q1. Q0 and Q1. For Q1, if 0 is the input, then it goes to the Q2, which is the final state. For Q1, if 1 is the input, then it remains in the same state. For Q2, 0 and 1 are the inputs means it again goes to the Q2 itself. So this is how we draw transition table for a given DFA. Next, without any late, let us go to non-deterministic finite automata. Non-deterministic finite automata, NDFA or NFA, is an automata in which for some current state and input symbol, there exists more than one next output state. It is also known as a non-deterministic finite automata or acceptor, NFA. So, formal definition. Non-deterministic finite automata is defined by the quintuple M is equals to Q, sigma, delta, Q naught and F, same as deterministic automata. So, formal definition of NDFA. An NDFA can be represented by a phi tuple Q, sigma, delta Q naught F, where Q is the finite set of states, sigma is a finite set of symbols called the alphabets, delta is the transition function where delta, here it is very important, Q cross sigma implies 2 power Q. For DFA we have already seen delta is equals to Q cross sigma implies Q, not Q naught. Okay, so for Q, it is DFA. If it is 2 power Q, then it is NDFA. So Q0 is the initial state and F is the final state. The graphical representation of NFA is same as DFA. So let us see an example for NDFA. Let us non-deterministic finite automaton B. Here they gave the states, inputs, initial state and final state. Then we can represent it in a graphical form like A is the initial state, B and C is the final state. So the transition function delta as follows. He gave the transition function, then we have to draw the graphical representation. So if the input for A is 0, then it goes to B and A. So 0 and 1. It is represented like this. For B, if the input is 0, then it goes to C. For C, if the input is 0, it goes to C itself and B again. And if for A, the input is 1, then it goes to B. For 0 and 1, we are having B as the output, next state of the A. And for B, if the input is AC, then it goes to, if the input is 1, then it goes to A and C. Not only one state, it is having two states for each input symbol. So this is known as NFA. Have you observed it? The difference between the NFA and DFA? Let us see the differences. The following table lists the differences between NFA and DFA. For DFA, the transition from a state is to a single particular next state for each input symbol. Hence, it is called deterministic. For the NFA, it is having multiple next levels, so it is called non-deterministic. Empty strings transition are not seen in DFA, but NFA have empty strings. Backtracking is allowed in DFA, but backtracking is not allowed in NFA. DFA require more space. NFA require less space. A string is accepted by DFA if it transmits to final state. A string is accepted by DFA if at least one of all possible states ends the final state. This is all for this presentation. So next we are going to see example problems for solving NFA. Here comes our first example. So here our initial state is Q0 and Q3, and if we give 0 as input for Q0, it goes to Q0 Q1. If 1 is the input for Q0, it goes to Q0 Q2. If 0 is input for Q1, then it goes to Q3. At input 1 for Q1, there is no next state. It won't go to any other state. It will be in the same state. For Q2, if 0 is the input, then it goes to Q2 and Q3. If 1 is the input for Q2, then it goes to Q3. For Q3, both 0 and 1 are Q3. So here we have written where it goes when the input is 0 and 1. So in the same way, we are going to write for the new states flow. Here is the transition diagram for the given NFA. Now, this is the second example for NFA. Here he is asking, design an NFA with sigma, like inputs are 0, 1, which accepts all string ending with 0, 1. So 0, 1 should be the final ending of the string. So we should design the NFA in such a way that it will accept all the. So now let us take the initial state as Q0. We can give any input like 0, 1, then it is no problem. It will be remaining in the same state. And if we give 0 as the input, then it should go to the next state. And if next state 1 is the input, then it should go to the final state. Without 1, without 0, 1, it should not reach the final state. That is the main motto of this NFA. So next example. Example 3. So design an NFA with sigma equals to 0, 1. 0, 1 are the inputs in which double 1 is followed by double 0. So here we need, for let us take the initial state as Q0. From there we need double 1. So next state is, it is going to next state when we give the input as 1, and it will go to the next state when we give the input as 1. So double 0. We need a double 0 immediately. So next state, if it should go to the next state, then we should give double 0. So then it will reach the final state, which is Q4. In this way, we should design the NFA. So hence the NFA becomes this way, which accepts 1100 every string which is containing 1100 continuously. So here is an example So if from q naught from q naught, if 0 1 are the input, it will be staying in the same state, or it is going to the next state, and next 1, and next 0 0, and it will accept the strings having 1 1 0 0 in it. So this is the final conclusion of this NFA. Let us go to the next NFA. So fourth example, design an NFA with sigma equals to 0 1, which accepts strings in which the third symbol from the right end is always 0. So this is somewhat typical. So first state, we can give any input. If it is 0, then next input can be anything and next input can be anything. Then it should reach the final state. This is the final NFA of the given condition. So at initial state, it can be 0 or 1. If it is 0, then the next two states can be anything, but it should end with last third digit as 0. So this is the NFA. So next we can see the conversion from NFA to DFA. So now let us see conversion from NFA to DFA. In this section, we will discuss the method of converting NFA to its equivalent DFA. In NFA, when specific input is given to a current state, the machine goes to multiple states. It can have 0, 1 or more than one move on a given input symbol. On the other hand, the DFA, when specific input is given to a current state, the machine goes to only one state. DFA has one move on a given input symbol. Let M equals to Q sigma delta Q naught F is an NFA that accepts the language L of M. There should be equivalent DFA denoted by M dash equals to Q dash sigma dash Q naught dash delta dash and F dash, such that L of M is equals to L of M dash. So this is the equivalent DFA for L of M, which is the NFA. So steps for converting NFA to DFA. Initially Q dash equals to pi. Add Q naught of NFA to Q dash. Then find the transitions from the start state. Third step is, in Q dash, find the possible set of states for each input symbol. If this set of states is not in Q dash, then add it to Q dash. This is a very important step. And final step is step 4. In DFA, the final state will be all the states that contains the final state of NFA. So if we do an example, you will get a clarity of converting NFA to DFA. Here comes our first example. Convert the given NFA to DFA. Here is the given NFA. So we can see here, this is the transition table of given NFA. If Q naught 0 is the input, then Q naught, it goes to Q naught. If 1 is the input, Q naught goes to Q1. For Q1, if the 0 is input, then Q1, Q2 are the output. If 1 is the input for Q1, it goes to the Q1 itself. For Q2, if 0 is input, it remains in the Q2. If 1 is the input, then it goes to Q1 and again it comes to Q2. So this is the transition table. Now let us see how they converted NFA to DFA. Here Q0 comma 0. Q0 comma 0 is Q0. Q0 comma 1 is also Q1. So these are already existing. At Q1 comma 0, it is going to Q1 Q2, but DFA can't go to the Q1 Q2, two different states at a time. So we are taking Q1 Q2 as a same state, and Q1 1, it is going to same itself, Q1 itself. At Q2 comma 0, it is going to Q2. Q2 comma 1, it is going to Q1 Q2. So Q1, Q2 is the new state generated. So for that also we are writing Q1, Q2, comma 0. Q1, Q2. For these two we have to see. Q1, Q2. Again Q1, Q2. So Q1, Q2, comma 1. Again Q1, Q2, comma 1 means Q1. It is going to 1. Q1, Q2. If 1 is input, Q1, Q2. So we match those both and Q1, Q2 is the final state. Next. In which Q2 is there, that is taken as the final state, which is represented with double circle. So here are the states in DFA: Q0, Q1, Q2, Q1, Q2. In this, Q0 is the initial state, Q2 and Q1, Q2 are the final states. So for this transition table, we will draw the transition diagram. So Q0, if 0 is input, Q0, and 1, if 1 is the input, it goes to Q1. In this way, we will draw the NFA to DFA. So this is the whole method, and that's it. Thank you for this wonderful opportunity. Thank you all.